Is streaming good? Can you?
As long as it's green, blinking green.
Yeah.
Cool. Then just go for it.
Yeah. Streaming should be good. Yeah. After some administrative stuff, let's start with the actual content. But like, first of all, I want to hear from you. Like, what's your expectations, or when you signed up for this, what did you have? Like, what was on your mind? Like, what do you expect from this? Did anyone read the course description, official one?
No, I'm interested.
Not really. It's just part of the bachelor I'm taking. So.
Okay.
I want to make games in whatever way I can. So for this to be here, I expect to be able to make like a very low fidelity roguelike game, sort of like Dwarf Fortress.
Okay. Like, let's brainstorm maybe. Games. Anything else? Yeah.
Will we learn how to work with translucent objects?
Well, that's not kind of part or like of the mandatory and key core part of this course. But as I mentioned, like by the end of the course, we have some room to fill based on our needs and interests. So if you're interested in that, yeah, it's my pleasure because that's what I'm actually working on right now. Yeah, why not?
The answer is yes.
What else? Yeah.
Well, I did read the course description, but I don't think I remember everything. But 3D maths and writing shaders like vertex and fragment shaders. And
Great.
stuff like that.
Great, exactly. Right. Shaders, yeah.
Will we be teaching how quaternions work in 3D maths?
We did it at the end of the last course.
By the end, right?
Yeah, but we can sneak it in earlier. Yeah, probably.
So yeah, we'll see. Like, depends on how enthusiastic that group is.
Yeah, I think we should talk about it. That's good that everyone gets away with quaternions. Ivor, what do you think? Quaternions, yes or no?
Yes, they would have been.
We have I think a presentation on that, but I think it was not included.
Okay. Anyway,
But there are some materials that we can cover. Yeah,
Yeah,
we
yeah.
have something at hand.
Yeah. Cool. Yeah. Quaternions.
Not covered in math for you guys.
Oh,
Quaternions? How is it?
is it covered in maths? That's a
It was covered in math.
transformations only. Okay. Right. Okay. Right. Cool.
Is it
Okay.
the right spelling?
Quaternions. QA. Whatever. You keep us.
Yeah.
It's correct.
Uh,
Quaternions.
or
Quaternions.
And there's an N here. It sometimes shows up.
Okay.
Quaternion. Whatever.
Okay. Yeah.
So
Those weird words, that's not actually English.
Yeah.
That's right.
it's
That's right.
Super technical, scientific kind of feel. Well,
Other things.
yeah, please.
Yeah, using like glue, GLFW, and GLM like colors.
Yeah.
Make the whole process a bit easier.
Okay. So just for the rest of the class, what are those tools for?
Well, it helps you to. There's that. Well, sometimes I mix them up, but I think Glue is the one that makes sure that uses the most up-to-date version of the OpenGL, I think, and GLFW is the one that lets you have inputs to the program, I think. If I don't mix them up.
Okay.
With names.
GLFW is the Windows system integration. So it loads up the window on your operating system and it gives you a surface from which you can render to from OpenGL, while GLFW just loads the function pointers from the driver, basically.
Yeah, so GLFW is the one that makes sure that uses the most up-to-date.
No, that's GLFW. And
Okay.
GLFW. No, wait.
Yeah, it's confusing.
Which was the other one?
There's glue.
Yeah, glue
Yeah.
is really
Yeah.
old, so
Yeah.
it's not really up to date and it's really buggy. So you should use GLAD if you want the most up to date.
Yeah.
But GLAD and glue is the ones that load the function pointers from your driver.
Yeah. There's names are so similar.
Cool. Yep.
Yeah.
Are we forced to use any of those libraries? Or can we use whichever we want?
So which one do you have in mind?
Can we use SDL, for example?
That's a tricky one. Should I answer that, or do you
I
want
already
to?
have render working with SDL.
Yeah, we will be primarily focused on OpenGL, but if you want to explore like even Vulkan,
No.
yeah,
He's,
but like
he's talking to, can he substitute GLW for SDL instead, right? So, and we have done that in the last year. The downside is that SDL abstracts quite a bit away from the messiness that you need to deal with if you have GLW, right, to interact with your system. So, and we found that people that use SDL actually learned less than GLFW in the actual assignment. So, I mean, if you really feel confident to suggest, yeah, GLFW has nothing new for me to offer, then you want to explore advanced features. One of the, or two examples or two advantages you have in SDL is that you have network support and sound, for example, right? Which you don't have in the other case. So if you really want to build on this, that's an option. But for the assignments, would prefer you clearly not to use that and rather fall back for GLFW. However, we can perhaps discuss it for the last assignment. If you show once that you actually can deal with GLFW, that you want to drift off and go into your nerdy corner and push the boundaries a bit, then I think there would be probably space for discussion in that, right? So, Demon.
Also, I assume that it's not that much input with the windowing system. I mean, mostly you'll be doing the OpenGL calls, and those are sort of the same if you're using GLFW or SDL.
Yes, but also it means one aspect, though, that's true. One aspect to highlight, though, since you're mentioning it, that the labs are mostly provided using GLFW, right? So for you, it would always be a bit of a overhead of actually, translating it to your framework. So yeah, but I think we're kind of
teaching assistants. It's also easier to.
There you go. That's a word of warning from the teaching assistants. With SDL, you're on your own. That's basically what you just said. No, but no, just kidding. But yeah, so you get the gist of what we're talking about. There's no harm looking at it, particularly for the advanced feature integration. Some students did this. They actually use both. They use GLFW for one thing and then SDL for advanced features, right? So use them in conjunction. Perhaps you can modify your framework to accommodate this, right?
Yeah.
So that answer your question somewhat?
Yes.
Okay. Sorry for the injection, please.
no, thank you. Anything else? Would you like to add anything? All right, I think we have pretty
Shaders, games.
interesting, very, very technical list. Last year, I think it was
More high
a
level.
bit general.
Yeah, so you guys know what you want. That's pretty good. And scary.
Yeah, focus, like, again, what will be the focus of this course, like terminology. We will have some terminology today, like later in this lecture, and like formats, frameworks to work with, like theoretical foundation that you need, like mathematical part for all like transformations, matrix manipulations, etc. Like technical part, C++ and OpenGL. So like if you want to explore like using other languages like Python, you can do that, but like for within this course we want to stick primarily to C++. Yeah.
Can we use C++ 17?
What compilers are we using? That's what features of 17 do you want? Do you want the language features or do you want the library features?
No, language features.
Language features?
What's the difference?
Can I answer when I know how the compiler support are for all the different platforms?
Yeah, sure.
At least you can at least use 14. That's well supported, and or at least I'm not taking that decision, but I assume so that there's no problem using 14. I think 17 has started to mature a bit, so probably most compilers support it. It's So I don't, at least the language features. So I would assume that it would work.
Yeah, the main thing is that you make your code work. Like we need the running code.
We don't want that much work. Like setting, we want to get to sort of, when we download your projects, we don't actually want to download extra libraries or potentially update compilers or those sort of stuff. Yeah, but 17 has been out for a while, and it seems like Visual Studio is pretty up to date, and so is
Clang
in
GCC.
GCC, as long as you don't look at sort of the parallelization and STL stuff.
Yeah.
So looking at it here, it looks like most of it should be, should be okay to use. So I would say go for 17 if you want.
Yeah.
Just don't go and use all the super obscure features that are not yet necessarily properly supported in all the compilers.
Yeah, for OpenGL, like theoretically for version 4 onwards should be okay, but we write 4.3 onwards due to Mac limitations. And the one important thing to bear in mind, like when you refer to OpenGL tutorials, just make sure that you're not using like tutorials based on OpenGL 3 or like older versions, because it won't work, and then you will like end up with some trouble. So like make sure that you're dealing with OpenGL 4 onwards. And yeah, technical part like pipeline, and as you already mentioned, like shaders, textures, like lighting, and physical part that comes later, and Outlook that can be kind of that flexible room. And what I can propose, like you have already mentioned some kind of small part of it, but very interesting one, like translucency and general material appearance, and Mitsuba renderer that is very simple and physically based for like photorealistic rendering of scientific tasks. So we can negotiate it later if you're interested in that kind of directions. Well, I think Christopher has already introduced like general outline of projects, like assessment forums. And yeah, one important thing that Christopher always highlights about this course, like start working from the very beginning, follow all the labs, because you need these skills, you need the competence, because the course is pretty tough and you won't just have a shortcut on the night before if you pull an all-nighter.
No way.
I could just add in that we tried doing that. Because we had other when I took the course, we had other stuff going on, and that ended up with and we did deliver, and it went great. But we had like a 5-week assignment, which we decided to do in 2 weeks instead, and that was 2 weeks where we sort of slept like average of 4 hours. So don't wait until the day before.
That's not going to work. Yeah.
Yeah, but on the other hand, I don't want to kind of scare you a lot. So if you follow all the labs, if you do all the like tasks during the lab sessions, you should be all right.
Yeah.
And yeah, we need working programs, and teamwork is already mentioned by Christopher. Yeah, programming, it's not just bringing a program that works. That kind of secondary outcomes that is pretty important, I think, is to improve your coding skills and also like coding standards, your professionalism, like documenting, organizing your code, and yeah, understanding all the pipeline, understanding the different requirements that you may face when implementing your solutions. And yeah, for group work, using Git, I think, will be very simple, and most of you have experience with it, right? Yeah, and integration of libraries, and it's very important to focus on the user. It's graphics programming. Your final, like, eventual goal is to make a nice display of whatever is modeled in the system, in the back end. So focus on the user, look at your output from the end user point of view and assess it that way. And yeah, we will have, like, later debugging that is important, like, for your work, and kind of document your work, because that will make your life easier, a lot easier later. Yeah, Christopher has introduced, like, principle, lectures Monday and labs Tuesday, so it's not very solid kind of plan. If we see that we need, like, more time for lectures or more time for the labs, we can be flexible about this too. And yeah, interactivity is appreciated very much, so I want to get your involvement, your kind of ideas, contributions, answers during the lectures. That will make it way more efficient, I guess. And it's going pretty good so far. Thank you for that. Yeah, we will propose some projects, but if you want something to do, like, if you're really eager for doing something, you can propose your own idea, and we will assess if it's kind of relevant for the course, and if it's comparable for whatever we have, you can do, like, your own idea then. Well, computer graphics, we have talked about your expectations, but particularly on computer graphics, what is the purpose of this all? Like, why are we doing computer graphics? Ideas?
Shows things on the screen.
Yeah? Pretty simple?
We as humans like pretty shapes, so it kind of matters that what we are looking at looks pretty.
It depends. From scientific point of view, not really, because you want that it was physically accurate, that it kind of replicates light transport, so you have, like, physically right result, not just pretty looking one. But it depends on your, completely depends on your application. Like in gaming, that can be one of the goals. Yeah. Anything else? So why do you need computer graphics? Why did you come to this course? Like,
Visualization.
Sorry?
Visualization.
Visualization, yeah.
You want things to actually look like something. You want if you want something to be simulated, or if you want something to have a specific appearance or a specific look about it, you need computer graphics.
Yeah, exactly. Visualization and appearance. Yeah. All right. Yeah. To look at it from very high level, what is the very high level pipeline? We have some application that creates need for, like, some object to be displayed, and we have particular geometry defined in space for whatever need we have and whatever object we have. Then we do have rasterization step that is simply converting this model into pixels, to pixelize it, to make it possible to be visualized on the display. And final step, when we have it kind of split down to the pixels, to visualize and, like, make it illustrate it on the displays. And this is more detailed and I think more understandable. So we have some shape defined. So we approximate it using some polygons. And any idea what is polygon? Yeah.
Simpler shapes.
Yeah, and what is a characteristic of it?
Triangles maybe?
Yeah, triangles are one of the examples. Yeah.
Shape, well, yeah, a geometric shape is defined by at least 3 points.
Yeah. That are connecting and that give this closed given defined surface. Yeah, so we approximate our shape by polygons, like vertices that are interconnecting with each other, that create some kind of mesh or facets that cover our original surface. Another point is light and matter interaction. So, okay, we do have the shape, but in order to visualize, all like visualization and vision is depends on the light, right? The light is source of vision, so we need to really care for light interaction, like geometry and like light, how it interacts with our object and how it is transported in space and in relation with our object. Next point, okay, we have light, we have our geometry, but which is the perspective we're looking at it? Like, it differs dramatically whether I look, for example, at this table from here or from Christopher's point of view or from your point of view. So we need all these transformations to make the right perspective we need for our application. And the next thing, clipping. If we model this table right, do we need to have like all the table in the memory? Like from my perspective, no really, because I don't see like around a third of it. So we need whatever just fits within the screen, the display. So we clip and we just show the one that is just within the field of view, just given field of view we want to see. And the final step, we have this in space, but don't forget, what is the kind of very, very important characteristic of display that we have to bear in mind, and that is kind of limiting? Yeah?
That is 2 dimensional?
Yeah, exactly. Displays, we have 3D objects. We want to have perception of 3 dimensions, but we have to do that using 2 dimensions only on the display. So we need to transform and translate this 3-dimensional model into 2-dimensional display and translate that to particular pixels that are present on the display. Yeah, so like as already mentioned, creating 2D and 3D images, displaying them on the 2D screen, and integrate with the software to have like some particular applications, like gaming, for example. Well, challenges. What are the challenges we might face within this pipeline from shape to displaying visualization? What are the obstacles and things that we have to bear in mind? Yeah?
Well, if you have a 3-dimensional shape, if you don't already have the code and setup to render it on a 2-dimensional screen, that might be a bit complicated, at least if you have a complex shape.
So transformation, yes, right transformation, that was already kind of part of the pipeline, that was meant to be there. But yeah, that can be pretty limiting our like capabilities. Yeah, please.
Yeah, I was thinking more that there's a lot of different hardware that the software might run on.
Yeah.
So
exactly.
That could be a problem. Something might not be supported on Mac or Linux. Something. So yeah.
Yeah, that sounds like very simple, but might make our life very, very hard sometimes. Yeah, that's a very good point.
Performance?
Performance, yeah, it's important. efficiency, performance. Yeah, like hardware varies. We have different platforms, and we have not mentioned mobile so far, but like the applications can be mobile, like why not? We were discussing just like Windows, Mac, Linux, but mobile can be one of the applications. CPUs, GPUs, they vary, displays vary a lot, like except for the technologies like CRT or LCD or whatever, like all the displays are unique in terms of their color gamut they can display, like all the possible space or like number of palette of the colors they can display, or the resolution. We need calibration to make sure that we reproduce colors and visual stimuli accordingly, like across different media. That's the problem. Yeah, software like operating systems, and when I looked at the last year's course, yeah, there have been lots of problems with Mac and Linux, like different people using different operating systems, different requirements. Programming languages, yes, but in this case I think we will stick to C++.
At least if you want to get a grade.
And also one fundamental thing that makes this look pretty complicated at first glance, because, well, when we talk, like think about our models, we think about objects like the final end results, and we don't really think about all the vertices, polygons, and all these kind of underlying low-level geometries, and it's like pretty complicated sometimes if you do not really try to get into depth and understand what's going on there. And yeah, performance has already been mentioned, very good point. And frameworks that automatize, yeah, this translation process.
I have a question.
Yeah.
I saw that you were writing about only displaying what was needed on the PowerPoint.
Sorry?
I saw that you wrote that the only process was actually displayed at the bottom there on performance.
Only process that is actually displayed, yeah.
Yeah, does that mean we'll be learning about culling algorithms?
Culling, whether it's included, not really, I think.
We didn't cover that in depth, no.
No, not really.
But you can put on the list of potential options there. We can talk about this as well, the magic list there. So.
Yeah. Yeah, like after some time we can discuss what you guys want to have in the later part of the course. Yeah, theoretical foundation, all these 3D objects, perspectives, translations from 3D into 2D, and frameworks and APIs that we already kind of somehow mentioned. Like you mentioned SDL, that is often used for 2D. OpenGL, that is primary focus of this course. DirectX, that is Microsoft version, like for Xbox or Windows. But if you like are interested in this one, you can feel free to explore. But like what is evaluated and assessed here, it's OpenGL. And Vulkan, that is pretty new one, and it's kind of opportunity and challenge as well, because we don't really know yet. It's like it's not experienced by the time, right? The stable version I think was released about a month ago, and it was like the very first version was 3 years ago. It's pretty low level. You need to do lots of things yourself, but Yeah, last year we had the talk about Vulkan, right?
We had Petra talking about Vulkan, so he was pretty immersed into it. Is there any Vulkan specialist here in this room? Yeah? Cool. So you're invited to give a talk about Vulkan in the class. Are you excited about this?
Possibly.
Yeah? Would you be interested doing that, probably?
Yeah, I can do that probably.
Yeah, that'd be cool. I mean, the later part of the course, because that's like what people usually want to look at, and you know, I think having an intro is really, really helpful to get the difference rather to OpenGL rather than that. So you know,
yeah, there's a lot of boilerplate code just getting a triangle working. I needed like 1,000 lines just to get one hard-coded triangle.
Wow.
Yeah.
So
I'm at 2.2 thousand lines now, and I can draw sprites.
nice, well done. So yeah, you seem to be well into it. So I think we need to talk offline and see where we can fit you in, because I think it would be really valuable to give the class some sort of appreciation. But I think we should do OpenGL first, so you know everyone has the same and some sort of basic understanding about graphics and graphics pipelines and how things work and so on.
Yeah,
And
OpenGL is a lot better for just learning how the graphics pipeline is working. There's a lot of details that you don't necessarily need to know in Vulkan.
It's also apparently written with a K.
Yeah, it is.
Yeah. Okay. All right. Hint. Yes. Okay. Well,
yeah.
you know.
And integration part, like
Cool.
combining with programming language, and we need to deal with input and interaction. And why? What does that mean to you? Like to deal with like input and interaction. Like most of you are gonna be game developers, right? So how do you relate graphics programming to gaming and game development? So okay, we have some visual stimuli rendered. We have like all the geometries and all the lighting interactions displaying, right? But it's just static. We need some input, some interaction from the end user, for example, to drive a car in a game. So to manipulate it from outside. That's our input. Essential for game development. And yeah, like multidisciplinary, like computer science part, programming, as I already mentioned, professionalism is appreciated and kind of secondary outcome to increase your programming and coding, not only directly skills, but kind of habits as well. Mathematics, as we already mentioned, 3D math, like geometries, all those metrics manipulations. And in the end of the course, yeah, mostly invited talks can be about physics, like light and matter interaction, all these shadows, material appearance, and like all the geometries and interaction of the light and transport of it. Well, what else we are gonna have today? Some simple terminology and image formats to start with. Yeah, here we are. Any familiar terms? Anything new?
The three on the top.
Sprite, right?
Yeah.
Okay, let's follow from the very top. Pixel, I think, is the simplest one. Just picture element. Pixel is the smallest element of the texture. It can theoretically be the same as pixel, but not always, because it depends. For example, if the texture is seen like from the very small distance, it should be stretched and should cover like several pixels. And on the other way around, if the textured surface goes far, this texture kind of is not distinguishable for the eye anymore, so several pixels can merge into single pixel. But as we have here, like informally, they can be referred to pixels as well. So when we have texture mapping, we will see like this more into details. And sprite is like any bitmap picture that is put on the screen. So that can be a small like bitmap put into the larger screen. Anything, any bitmap that is displayed to the screen, whether it's like a scene or just like small part of it. Bleed, copying of the memory over another one. So it's kind of overlay of several layers and like overwriting in the memory. So I will like show you like this slide. When we want to have that feel and perception of depth, what should we do? We have just background first, and then we have another plane that is closer than the background, so overwritten on that, and then we have another one. Then we have like the foreground overwritten on the back ones, and finally we have head-up display, like stuff that are on top of everything, like your scores, time in the gaming, and your level, and that kind of information. So when we have this kind of layers from farthermost one to closest one, we are overwriting information of this one, overlaying on the back layers. And that's what bleeding actually means. Parallax. Parallax, as you like read, is perceived slower motion of the distant objects. For what? Again, for depth and 3D perception. And can you bring any example? Yeah?
I know two examples. One of them just in video games, that the background goes slower. Yeah, like the background does go slower. The character to foreground moves faster.
Yeah,
you
yeah.
also use parallax scrolling on like website design. Some people use it.
Yeah, exactly. Yep, please.
Yeah, if you look out the window and move your head, you can see that the window moves more than the hill outside.
Yeah, that's inspired from human visual system.
It can also be used as a kind of cheap, instead of tessellation, basically by using a height map, you can translate certain parts of a texture faster than others, so it looks 3D when you're moving. It's a part of shader stuff.
Yes, that makes sense.
Yeah.
Any other point? Yeah, I have like a video of if anyone still doesn't exactly understand what we mean with that. Oh, come on. So, for example, this very old arcade game, Time Pilot.
I write pretty much all day, every day.
Sorry. Yeah, the thing that we just discussed. The airplanes in the foreground are moving very fast, while the clouds in the background, as you see, are slower, and this makes us creates kind of perception that clouds are a bit farther, as in reality, like as you mentioned, very good point, that window moves faster than the mountain. So that's a trick used for perception of the depth and of the 3 dimensions. Yeah, nice one.
The latest OpenGL.
Yeah, palette is just like array of colors available for the sprite. So like for the bitmapped image that is put on the screen, what are the colors at our disposal? Projection is how do we translate these 3 dimensions into 2D. Yeah, the last 2 points I will skip them for now because they are very OpenGL specific stuff, and we will have them later. We had this, yeah, parallax example like in the cartoons, and these kind of different layers that we have already mentioned, and side scrollers. Does anyone know what are side scroller video games? Yeah,
Made a couple of them myself, so in Unity, but yeah.
yourself, your games.
Yeah.
So can you explain what does it mean?
Side scrollers just you move a character along a path, just two-dimensional. You walk one direction and you encounter different objects, like you can move around the 2D labyrinth or jump through some.
Yeah. So you have a side view. You look to the whole scenario from the side, like for example, Pac-Man, and non-side scroller can be like 3D feel, for example, any first-person shooter games that you have kind of 3 dimensions. Well, earlier games, how they were developed, the way they were developed were inspired from the memory limitations, because memories were very small and they had to overcome these problems. Nowadays, they first kind of design the game and then they think how to make it efficient, because memory is not that small anymore. But yeah, earlier when memory was extremely limited, what kind of games did they do? Like screen-based limiting of the memory, when you have just like whole game is within the given screen and you don't go beyond it, like it's a Pac-Man example, yeah. And when you go to the next level, it just new scene is loaded, and if all the gameplay is just like beyond one single frame, the idea is to guess what comes farther, to work out like which bits you need to preserve and which you don't need, and faster you do this, better for processing and memory. So in this case, we are not limited to a given scene, but we are like moving still on this given plane, as you mentioned, and it can be either driven by a user, like the airplane. So we have this sky, we know what comes from here, we know what comes from here, and we just orient our airplane. And it can be time driven, when your object is moving across time, and you know like that from after this scene comes this bit, and then come whatever bit. I will show you example like to demonstrate what I mean. Saxon. Yeah, in Pac-Man you have just a scene that does not change, you are just within that. But in this case you have lots of things like that are coming into your display and then disappearing and coming, and you know what comes like when the time passes. And you can save memory that way. It's actually even simpler example to me would be, you know that game when Google Chrome is offline? So as the time moves, your dinosaur moves and you have to interact. Well, okay. And yeah, now let's move to the image formats. Well, what's key difference between raster-based image and vector-based image, and can you kind of name their pros and cons? Any ideas or experience? Yeah.
Vector-based images are mathematically perfect, and you can zoom as much as you like. You lose no detail, but they're less flexible, especially in terms of filters and effects, than rasterized images.
Yeah, you can
like
scale. It's mathematically defined.
Mm-hmm. But the raster images have a resolution. They're a fixed resolution. Yeah, you cannot zoom forever. without losing detail, seeing the individual pixels.
Yeah, when you zoom, you get artifacts.
Yeah.
Yeah, so like for raster images, we have predefined pixel. So it's kind of grid of pixels with values in each of them, while vector-based formats just define that mathematically. They define the lines, they define the directions, and if raster formats have this big disadvantage, why are we interested in them, and why do we use them at all? What is kind of very significant part of having raster images? Yeah, please.
I guess it takes away less processing power, calculating power.
Not necessarily. Depends on the resolution, I think.
I'd like to say that raster formats are way less work creating than vector formats if you're making something high fidelity.
Could you repeat?
Like, for example, very modern games, like you can't have a vector for each, like, little detail in, like, of all the, like, individual.
Okay, if you have very, very fine details, you need like very high number of vertices to define that surface.
Yeah.
And vectors, like you need lots of different vectors changing directions all the way.
Yeah.
You mean that? Yeah, but like very, very fundamental thing.
Memory usage. Like rasterized, you can compress them, make them smaller, maybe take less.
You can compress, but yeah, that's especially today. That's not the major thing that makes us kind of work and discuss that.
You can load them into the graphics card. They're easier to load, I think.
Not really, I think.
Yes, I can just guess. Maybe if you know it's not going to change on next frame, you can just use the same line. Just leave the image loaded. But I suppose you can do that with vectors as well.
You can do that with vectors. If something is kept from one frame to another, yeah, you can keep both ways, pixels and vectors. Well, yeah, fundamental thing that is very important is that our hardware, like especially displays, are raster based. We don't have vectors on the displays. We have pixels, and whatever we have finally, it should be. Do you remember this slide?
Yeah, so it's automatically transformed.
Yeah, it should be rasterized anyways.
Rasterized anyway.
So because of our hardware limitation, at some point we need to convert it to pixels to make it to visualize it on our display pixels. That's very important point, actually. Yeah, some formats, some like very old and outdated formats like PGM, that is just plain text, and we will have an example on the next slide, and color plain text, Windows proprietary bitmap, some formats that involve lossless compression, like GIFs that are nowadays primarily for animations. Have any of you worked with like still static GIF images? But yeah, that's not the most popular format for that. And PNG, that is kind of standard and open source and very widespread. TIF, TIFF, and RAW, that is device dependent and depends on the manufacturer and all of its parameters. And another very established standard with very good compression capabilities. Actually, PNG is also good at compressing homogeneous areas, but JPEG is like lossy compression. but it is based on the characteristics of human visual system. Well, let's see first PGM. It's like plain text means that, okay, what do we have here? We have a header. We have a header, so like this is a version. Second version, we have the name of the file. We have the resolution, like physical 2D resolution, and we have the grayscale levels, like highest possible value, and then it's just like pixel wise, it's a grayscale format, and for like each pixel we have just given intensity. It's not a very wise way to store the data because it takes too much space, right? So JPEG is a standard since the beginning of 90s. It's 24-bit encoding, and can you guess how many colors can we have with this?
3.
Nope, 24 bits. Yeah?
16.8 million.
Yeah, exactly. And it has lossy compression that is inspired from human visual system, and I will explain why. And it can decrease file size dramatically, and for that reason, actually, for yeah.
I was just wondering, is it this Unite can like only view like 10 million different colors? I think, if I'm not remembering incorrectly. So why use so many values?
Well, that's an open question in color science.
Yeah,
how many?
My memory from organic chemistry, but I'm not.
Yeah, there is no fixed number. So there are like 16 million values that you can have in JPEG.
Yeah.
But how many of them people really perceive, that depends on like lots of different factors, and that's still like open question, that there is no fixed and given number that.
Yeah, you can still perceive data as colors. I think it's like, can you perceive the difference between two very similar colors?
Yeah, that's it depends. Like, also depends on the colors. Like, have you seen Mansell ellipses, where like there is the color space and there are like ellipses drawn, and the colors within the ellipse are perceived as same color by the human observer, and the size of the ellipse changes dramatically depending on where in the color space you are. So to some colors we are more sensitive, to some colors we're less sensitive. It also depends on like your sensitivity. It depends on illumination spectrum. But yeah, there is of course the limit after which we don't perceive the color difference anymore. But that's very tricky thing. So we can't take color difference and generalize for all cases, because it's very complex phenomenon, and it's very it's very situation specific. And actually now one of the biggest challenges in color science is producing perceptually uniform color difference formulas, because if you there are like lots of color difference formulas, like delta E74, delta E2000. They have like different ways of calculating color differences. For example, if we have color with the given coordinates and another color with given coordinates, we calculate, for the simplest way, delta E74 is just finding Euclidean distance between the 2 points in 3D space. But the trick is that larger distance does not necessarily mean larger perceived color difference, and the other way around, smaller, so it's not really correlated well with perceived difference. That's a problem. Our perception is super complicated. But yeah, of course, like at some point we stop perceiving the difference. But a tricky thing is actually that there are few people, at least mentioned in the literature, that are tetrachromats. So human vision is like based on trichromacy, right? We have 3 different photoreceptors, and people who are color deficient have like 2, on extremely rare cases 1, and there are people who have like 4 different photoreceptors. That means that they see more colors than we ordinary people do. So it's like very physiology dependent as well. Yeah, where we were. Yeah. And yeah, file formats for JPEG, like header, identifying the format, compression, quantization tables that we use for compression, and I will explain here what does it mean. The content itself, the values for the pixels, and application-specific data like EXIF, where we have all ISO, aperture, and all these kind of parameters that were used during the shooting. And how does compression work? First of all, we have like some range of brightness, but human vision is not really sensitive to all of them, so we downsample, just cut it into normalize within some range that is sensible. Then we split this into blocks, and mostly it's 8x8 blocks, and we continue processing further on these blocks individually. And what is the human vision characteristics that is very important and very wisely used here? Our vision is very sensitive to changes in low frequency domains. So when the variation is low, we are sensitive to changes, and when we have high frequency areas, like when the variation is large, we are not that sensitive to the changes. For example, Christopher had great example, like if you look to the dark forest over there and the snow, the difference is very large, and if you like decrease this difference by like several steps, you don't really see that much. But if you have homogeneous wall here and you have like some shades, and if you start changing these differences, they are small anyways, so you will see that more clearly. Or if you have like shades on the snow due to surface irregularities, you have like very tiny difference. It's almost homogeneous, so if you start changing these values, you will see that immediately, and that's what you utilized here. So here they use discrete cosine transforms to transfer these values into frequency domain, so like high frequency data, low frequency data, and then quantization tables come into play, which divide high frequency data like by larger numbers, and low frequency data that we are more sensitive by smaller numbers, and finally we end up in very high frequency areas which we cannot see anyways with zeros. And then after this division, it's rounded to the nearest round number, and that's where most of the loss is coming from. So to make it very simple, just putting aside all those terms to make it super simple, if we can't see the difference anyways, why do we need all these values? We can just discard that if we do not see it at all, or if it is not that disturbing, and if we are happy with the compression even for like very insignificant artifacts. So it takes into consideration what we see and what we don't, and discards whatever we don't see, and compresses the image. But and final step is entropy encoding. That is simply just like calculating the statistics, and the most popular frequencies or values are coding with the cheapest way possible. So if, for example, level 50 is most popular and covers half of the image. We encode it with fewest possible number of bits. And if we have like very rare values, we use like more bits to encode that. And in that way, popular ones are encoded in a cheap way. And yeah, compression does not always work perfect. As we see here, like it has its limits, and finally, because we compressed the chrominance channel as well, we lost the colors completely. We started seeing these 8x8 blocks, and when removing too much high frequency data, like we starting getting something very homogeneous, homogeneous areas with just like small number of colors. But on the other hand, like we have very significant amount of memory saving, like it's around 36 times approximately. Yeah, and vector formats, so they are mostly XML based, and like EPS is PostScript, but like mostly we have I will go faster because we're almost over time. Yeah, SVG is like XML based, but inside you have CSS implementation, JavaScript, you can index it, you can search it, and it can be interactive. I will show you examples, and yeah, we have like supported operations like masking, transformations, but like the most interesting thing how this vector format looks like, I will show you on the example. Yeah, here you are. You can like zoom in, zoom out without any artifacts, but the coolest thing here is that look how it's represented. It's an XML. You have some CSS styles, and then there are like per country. For example, let's see Norway. Yeah, this is how Norway is defined. So we have a starting vertex, a starting point, and then we have a next coordinate this is connected with, and then these coordinates create the outline, the shape. So instead of having separate pixels representing Norway, we have these vertices that are interconnecting in this sequence, and they finally make the outline of Norway. And that is the case for all countries, rivers, etc. So this is how this vector, so we have these vectors that define our objects in SVG. And for interactivity, we have another example like this toy train, and we have animation supported here. Well, we almost reached the, sorry, we reached the end. Yeah, and SVG-Z is just zip compressed version of it. Yeah, finally, the resources. Actually, there are like, I would say, two ways of learning, book-based and tutorial-based. If you feel comfortable with the book, you can purchase electronic one for around 65 crowns, but it's not kind of any requirement or anything. It's just up to you how you master with OpenGL. Mostly there are like lots of very cool tutorials on the internet. Like there is OpenGL tutorial that is, I think, mostly for advanced stuff, but be careful to work with fourth version. Yeah?
The OpenGL tutorial there is, I think or is this the learnOpenGL.com or is it just OpenGL tutorial?
I think both.
Yeah, because the Learn OpenGL tutorial is that's up to date and that's really basic, sort of for everyone to get into.
Maybe we can add that to the wiki.
I get to the wiki, yeah.
We can get to the wiki. Yeah, Anton's OpenGL and SIGGRAPH 3-hour YouTube video with pretty cool explanations. If you can like watch a 3-hour long video, it's pretty nice one. And yeah, task for tomorrow, update graphics driver. And if you download this software, download OpenGL, you can very easily check which OpenGL is supported in your system. And in any case, if you like upload your update your driver, you will have I think 4.5 support. Or I can show anyways. Oh. Taking so long. Takes too long. I don't know why. Okay, you can like check this software out yourself.
Anyway, you can continue with that. Yeah, you can just figure out if your graphics driver supports.
Yeah, we can take care of all those stuff, like maybe
tomorrow
to make sure that everything is running.
Yeah. So, but if your graphics driver doesn't support it, there's this OpenGL extensions viewer. In many cases on Windows, it will show you the latest OpenGL version that's supported. On Linux, you saw the instructions there. You need to download Mesa utils and run them. They show you the OpenGL renderer, and then you know that you are on board, or you know that you are at a later stage or not. But we can continue with that tomorrow. It shouldn't be a long task anyway.
That's what I'm trying to run right now. But oh yeah, finally I got it. Yeah, this is how it looks.
Oh yeah.
So it gives all the information. Like I have integrated.
So you see OpenGL version 4.5 there, for example. Yeah.
And DirectX.
Yeah. On Vulkan as well.
Yeah.
Just a quick question. How many here are sort of feel familiar with debugging in Visual Studio, that are like comfortable using breakpoints and potentially also conditional breakpoints?
The first one I've used.
Yeah. Then maybe your etc. Okay, that's a lot. Would you guys still like to have, or would the people still like to have a sort of debugging session to learn the basics of using breakpoints and stuff? Because that will be quite valuable for the graphics.
Sure. Can I suggest the opposite? Who hasn't heard about it? Because that seems to be more sensible to actually bring those on board, right? So, because I think it's.
I've heard about normal breakpoints. I've never used conditional ones.
That's reason enough to put it into the curriculum.
Then we'll do next week the debugging.
Sounds good.
But, yeah.
Will you be teaching how to debug the draw calls from GL?
We'll be getting to that later when we actually start introducing GL.
Which debugger are you using?
We'll be looking at RenderDoc.
Yeah, nice.
And some custom debugging tools.
Yeah.
Cool. Cheers.
Thank you.
Well, thanks everyone.
See you tomorrow.
See you tomorrow, and bring your laptops. Or any other machine that is terrible.